Welcome to this fourth part of digital electronics tutorials. In the first part, we have discussed on the number system, especially the Boolean algebra, and we have also discussed on how to reduce the Boolean algebra expression using the truth table and the use of complements. We have discussed the expressions involving the SOP and POS. We will take the discussion forward with the universal gates. So universal gate basically the two important gates. One is the NAND, another one is the NOR. These two gates are basically known as the universal gate. So what are the advantage of using the universal gate? They are economic as they are cheaper to manufacture using the single gate type. Also, they are simplicity, which is because of their easier IC design and production. They are versatile, can implement any Boolean function. So any Boolean function means we will see like the AND or NOT, all this basic operation we will get using this universal gate. And in terms of the speed, they are often faster than their corresponding equivalent AND or circuits. So the implementation strategy for NAND realization, we will express the function in the SOP form and we will apply the two-level NAND logic. Whereas for NOR realization, we will express the function in the form of POS, that is product of sum, and we will apply two-level NOR logic. So for NAND, we will use the SOP, that is a sum of product, and for NOR, we will be using the product of sum form. Let us understand first using the NAND gate how we can obtain the basic gates such as the NOT, OR, and AND. So when you have the NAND gate, you connect both the input together. So you have A.A and then you apply the complement, you'll get the A complement, that is the output Y. Whereas for the NOT input, then NAND if you are using, then Y is equal to A0 dot B0, and then overall we are using the complement which is A plus B. So this is in accordance with De Morgan's theorem. NAND followed by NOT if you are using, then A dot B and double bar we are using, then we are getting the same form A dot B. And the key insight is that NAND with inverted input will be giving you the OR gate. Whereas the basic gate using the NOR operation, if we see, first we'll see the NOT operation, then connect both the inputs together. So we have A plus A, and then we have the NOT operation, so we get A bar. AND operation, NOT input, then NOR. So we have Y is equal to A bar plus B bar, and then we are using the NOR. So we get A dot B. And this is in accordance with De Morgan's theorem again. NOR followed by NOT, we will be giving you the OR. So here you have A plus B bar and then you have the bar. So we are getting the A plus B. So the key insight is that the NOR with inverted input will give you the AND gate. Problem number 37 of this tutorial series, where we will see the NAND gate realization in a simple problem. So the problem is you have an expression where F is equal to AB plus CD. You have to use only the NAND gate. So you need to implement this expression. So the solution step with the step 1, the function is already, if you see, in the form of SOP, that is sum of product form. So you can apply the double negation with help of De Morgan's theorem. So the function AB plus CD, if you apply the double negation, we are getting AB bar, then dot CD bar, and then the bar which is already present. So the NAND implementation structure, we have two labels. Label 1 where you have the NAND gate 1, input is AB and the output that we get is AB bar. So here this is the first gate 1, and in the gate 2 you have the input CD and you are getting the output which is CD bar from here. And level 2, the NAND gate 3, the two inputs that we have got it here, AB bar and CD bar, we will be taking and then we'll get the output as F. So the total gate required, if you see, we will be requiring 3 NAND gate, and this circuit is 2-level NAND implementation. Problem number 38, where we have the NAND realization, 3 terms we will see. So now the function that we need to implement, we have 3 terms, AB plus A bar C plus BC, and we have to use only the NAND gate here. So what we do is that in the step 1, we apply the double negation for this one. So here we apply the double negation for the original expression, and then we apply the De Morgan's theorem. So all these summation will be converted to the corresponding product, and the corresponding you will be getting the terms with the negation. So NAND implementation, again we'll have two levels if you see corresponding to this one. So the NAND operation of AB will give you AB bar. The NAND operation of AC will give you A bar C, and then we have need one NOT gate also to obtain this A first. Then we need the NAND operation of BC will give you BC bar. And finally in the level 2 we will get all the outputs connected together to have the final implementation in the form of F. So how many gates do we require? 1 NOT gate and 4 NAND gate. So total 5 gates we required for this particular expression to being implemented. Problem number 39, where we have the NOR gate realization in a simple terms. So the function that we have is basically A plus B and then multiplied with C plus D using only the NOR gate. We need to implement this function. So the step 1, where the function is already, if you see, this is in the form of product. So it is in the product of some form. If it is not there, then we need to convert. You can apply the double negation here in accordance with De Morgan's theorem. So we have the double negation, and then the product may be converted to the summation, and its corresponding structure will be obtained. So NOR implementation structure, we have level 1, where you need NOR gate 1, which is involving the input AB. So this is the A plus B bar, and the NOR gate 2, we need the input C and D. So here you have the output C plus D bar. In the level 2, where the NOR gate 3, inputs from gate 1 and gate 2 will be combined to form the output F. So total gates required, if you see here, we will require the 3 NOR gates, and it will be 2 level NOR implementation strategy. In the problem number 40, where the NOR realization we will see in terms of multiple terms. So you have A plus B into A plus Z, and then you have multiplied with B bar plus C. And this function we need to implement using the NOR gate. So how many steps do we require? So let us see the first step. You apply the double negation for this one. So here whatever the product is there, you will be getting the summation afterwards applying the De Morgan's theorem. So here you are basically applying the double negation. So all this product term is converted to summation here, and you are applying the De Morgan's theorem and splitting these terms from product to summation. So NOR implementation level 1, if you see here, A plus B bar, that you get from NOR of AB. A plus C bar we get from NOR of AC, and B bar plus C. So this B bar we need a NOT operation, and then the other one we require the NOR operation of this one. So total these gates output we need to connect it in the level 2 to get the output F. So total we have 1 NOT plus 4 NOR. So we are basically having 5 gates in total required. In problem number 41, where the NAND implementation we will use using the XOR gate. So implement the XOR function. So here you can see the XOR function that you have, which is the function involving two variables A and B. So A B bar plus A bar B, which is represented by this symbol. And we use NAND gate here to get this implementation. Method 1, either you apply direct from SOP, and we can see that we are applying the sum of product here to get this expression with the proper NOT operation. So the implementation strategy says that the NOT gate we will require, because here we have A bar, B bar and 2 NAND gate with tied input. Then the term 1 we will get, the first term that we have is the NAND gate of A and B bar. And the second term what we have is basically the NAND of A bar B. And then finally we can connect these two to get the F. In the method 2, we can efficiently obtain using 4 NAND implementation. So we need 4 gates here, and these gates are basically used in the NAND form of AB. So we get output X, which is equal to A B bar. Then these X will come here, and we can use the NAND operation with A. So this is the output. So that output is Y. and NAND of B and X will give you the output Z, and NAND of Y and Z, so this Z will come here, will add the output F equal to A or B. So minimum we required 4 NAND gate for this particular case. Problem number 42, where we need to convert AND OR to NAND. So convert the following AND OR circuit to NAND. So here you have the function which is to be implemented, and these function can be implemented using different steps. So step 1, simplify first if possible. So if you can see these terms, we need to simplify. So then a simplified form of this term we will be getting in these multiple steps. We have already learned this in the previous tutorial how to simplify it. So we'll get C into A plus B. Then in the step 2, you express in the NAND form. So we are taking this expression now and then we express in the NAND form. So this is what we are getting, and splitting it in this proper format, we get this one. And then step 3, we can use the NAND implementation. So we have NAND of AB, which is we'll be getting this expression with both inverted, that is OR operation, and NAND of C and output of gate 1 will give you the final output. So in general, we require 3 NAND gate, 2 OR gate and 1 AND gate. So that will form the NAND operation. If you have the multi-level NAND implementation for problem number 43, if you see this function, there are multiple groupings of the variables, and the variables are A, B, C, D and E. You have to using the NAND gate. So this is a multi-level function. So you first identify the level. So here the level 1, if you see, this is AB, and the level 2, the multiplication of A, B and C. Level 3, if you go deeper, you'll get A, B, C and D, and then level 4 you get up to the E. So step 2, you convert each label to its NAND operation. So AB can be obtained NAND of AB followed by the NOT. So 2 NAND gate we will have ABC, NAND of previously with C and then NOT operation. So 2 NAND gate again, ABC plus D required OR implementation with NAND, and finally AND with E will give you NAND then NOT. So how many gates do we require in total? Total we required 7 NAND gate. So note here that direct NAND conversion works best for 2-level circuit only. If we have the NOR implementation from the truth table for problem number 44, let us see. So here we implement using the NOR gate. So 3 functions are there, ABC, and the max terms are given. That is the product of sum. We have 0 to 46. So write the max terms what you have, 0 to 46. This we have learned how to write it in the previous tutorial. And write this max term and then convert to the product of sum form. So this is the product of sum form, and then you apply in the third step the De Morgan's NOR functions. So that is what you get it in the De Morgan's form. Now the implementation. So level 1 you have 4 NOR gate, 1 for each max term, and level 2 you will have 4 input NOR gate for final output. So total how many gates do you require? 2 NOT gate, 5 NOR gates. So total we required 7 gates. So but this is not in the simplified format. If still you do the simplification, you'll get F equal to C. Then did only the inverters that we have. So this simplification you can do it. We have completed all the tutorials. Now we will summarize what we have learned. So the first part we have learned on the number system. So the key concept that we have covered is basically the binary, octal, decimal and hexadecimal system. How do we convert one form to another, all the bases. Direct conversion can be possible, binary to octal and octal to hexa. Quick conversion tips, you can do it. Binary to octal, group into 3 bits. Binary to hexa, you can group into 4 bits. Any decimal, if you want to convert, then positional weight you use it. A decimal to any, you can use repeated division. So these tutorials on number system we have seen, and then we have seen on binary arithmetic and complements. Binary arithmetic we have seen the addition, so simple carry propagation method. Multiplication use shift and add method. Subtraction use complement method. So complement we have used 1s complement and 2s complement. So in 1s complement we have flip all the bits and end around carry we have taken, and then add 1 to the 1s complement, that will be the 2s complement. That is mostly used in the computers. So no carry in the result, then you will have a negative answer. So this you need to remember. We have seen the logic gates. So 7 logic gates we have seen from AND, OR, NOT, NAND, NOR, XOR, as NOR, and their operation, their symbol we have seen, and how do we convert from one to another. And in this tutorial we have seen the universal gate NAND and NOR, which are can be used to convert in any basic functions. And the Boolean algebra, the essential laws are very important. All these laws that we have learned: identity law, null law, idempotent law, complement laws, commutative laws, associative law, distributive law, absorption, De Morgan's theorem, and consensus theorem. So these laws are important because you need to simplify the expressions in a complicated form into simpler format. De Morgan's theorem is the most important, where you have the summation and then the NOT operation. It is converted into product form, and if you have the product form, you can convert into summation form. So this break the bar and change the operation. So these two De Morgan's law, first and the second law, is was important to solve any problem related to digital circuits. Two important forms we have seen: the standard forms, sum of product and product of sum. So in the sum of product, we have OR of AND terms, use min terms, where the function is equal to 1, and 2 level AND OR circuit we are getting. Whereas in the POS form, we have AND of OR terms, so function we are taking to be 0, and this is the 2 level OR AND circuit. In terms of relationship, the small cap letter M and the indexes terms will give you the mean term, and the product will give you the max terms. So this here we have the remaining indices which is not present in the mean term. Universal gate implementation, we have seen the NAND realization and the NOR realization. So in the NAND realization, it is best for SOP. In NOR realization, this is best for POS. 2-level NAND structure is used for NAND realization. 2-level NOR structure is used for NOR realization. And you can apply the function like this, where you have multiple variables. So here you have the product form, and you can have the summation format in the pump side. So the strategy is simplify the Boolean expression first, choose appropriate form SOP for NAND, POS for NOR, and then apply double negation as well as the De Morgan's the laws. So the practice tips are: for better understanding, always verify the conversion by converting back method, draw the truth table for complex Boolean functions, practice simplification using multiple methods, verify gate implementation with truth table, master De Morgan's theorem. They are everywhere, can see in the digital circuits. Some common mistakes to avoid is that forgetting generally the end around carry in the 1s complement, incorrect grouping in generally the binary, octal, and hexa conversion, misapplying the De Morgan's theorem, not simplifying before gate implementation, and confusing the min terms and max terms. So if you avoid these mistakes, you may be able to solve all the problems correctly. So that completes our tutorial series on digital electronics in 4 important parts. Thank you for now.